today is Nahuel Barrios. He's a guest of IFT until when?
Until today.
Until today, okay, so it's the very last moment. So, as usual, let me introduce our speaker. So, Nahuel got his PhD in a joint position between Institut Polytechnique de Paris and the Universidad de la República in Uruguay in 2022, in September 22, so let's say 2 years ago. And from that moment, he's, let's say, having a teaching position, an assistant professorship position at the Facultad de Ingeniería, the Universidad de la República in Uruguay. But he is also a postdoctoral researcher in Universidad do Estado de Rio de Janeiro, so not so far away. He's an expert on QCD, right? And his talk today is about a minimalist approach to low-energy QCD, the Curci-Ferrari model in Landau gauge. Okay. Nahuel, the floor is yours.
Thank you, Daro. Well, good afternoon, everyone. So let's begin with the overview of my talk. First, I will give you a very basic introduction about the strong interaction. Then I will explain a little bit why the low energy regime of QCD is important and why we still face challenges to understand it. We'll present afterwards the Curci-Ferrari model as a very useful tool to access this regime, and I will show you how useful it is by showing you results concerning correlation functions. In particular, in the case of the Yang-Mills theory, I will show you results. I will show you results on 2-point functions, on 3-point functions here, the Gauss-Gluon vertex and the 3-Gluon vertex. Also results on 4-point functions, and finally I will present you some results in the presence of quarks. So let's begin really with very basic stuff. So let's assume that we only know the electric force, right? And we are thinking about the atomic nucleus that is composed by protons and neutrons. We know protons have positive electric charge, neutrons do not have electric charge. So in principle, they would repel each other. So the question is, well, if I only have this force, why the nucleus is stable? And this is because, of course, there is another force that very originally we denote the strong nuclear force. And this force has very peculiar features because if these two charges are very close together, they repel. It's a repelling force around 0.7 femtometers. If we separate them a little bit, this force is attractive, and it becomes strongly attractive here around 0.8 femtometers. And then after this distance, it decays exponentially, so the electric force is dominant again if we separate these charges, right? So protons and neutrons are bound together inside the atomic nucleus by this force, the strong nuclear force, but this force is actually the manifestation of a more fundamental interaction. And this was quite clear in the 50s and 60s of the 20th century when a big amount of subatomic particles, quite similar to the proton and neutron, these are called the hadrons, started to appear. We had a lot of them, and they formed these very peculiar and beautiful structures, right? And here, essentially, what we have in the horizontal axis is the electric charge, and here we have another quantum number. It doesn't matter for this talk, but the thing is that we had these structures, and these structures seem to indicate that we have another property, a more fundamental entity there playing a role. And this actually was proposed in 1964 by Murray Gell-Mann and George Zweig, when they proposed the quark model to explain for this, right? So in this quark model, the hadrons are made of quarks, and these quarks interact via the gluon, right? So the quarks nowadays, we know that come in 6 different types or flavors, and they have very peculiar properties as fractional electric charge. So in the 60s, this was a very bizarre feature, right? So people were quite skeptic about the existence of quarks, but the very first evidence of the existence of these entities appeared in 1968 at SLAC in deep inelastic scattering experiments, where essentially you have a nucleon, and you hit this nucleon with a very energetic electron. If your electron has a lot of energy, then you have better resolution, you can see shorter distances, and then you could see that these nucleons actually had an internal structure. But at that time, this external structure, still people didn't know if this internal structure corresponded to quarks or not, so they were called partons. And later, in the 70s and later on, partons and quarks merged together, let's say, and now we know that partons are indeed quarks. Quarks and gluons carry color. This is the name of the charge, let's say, of the strong interaction. And this is why we called quantum chromodynamics, or QCD in short, the theory that describes the dynamics of quarks and gluons. So one of the most remarkable properties of QCD is the confinement. This is that we do not observe quarks and gluons in isolation. We cannot detect them. They are always composing hadrons. And in a very simplified picture, this is just a toy picture, let's say, we can say that we have mesons that are composed by a quark and an anti-quark. And this meson has no color, but the quarks inside it do have color. And we have baryons that are essentially made of 3 quarks. And we have other more exotic structures also as well. We have glue balls, for instance, or tetraquarks as well. So we have confinement, but we can heat this hadronic matter. We can increase the temperature and reach extreme temperatures, and then we will face a phase transition, right? We will have here a quark-gluon plasma. This quark-gluon plasma is believed to play a crucial role in the early universe physics. And there are still many things about this phase diagram that we do not know. Essentially, there are things about confinement we do not know yet. There are many things about this phase diagram we do not know yet. And QCD at low energies would allow us to understand better this phenomena. So let's be a little bit more formal, right? So QCD is a quantum field theory, so as such, it is described by a Lagrangian, right? This Lagrangian has 2 terms. The first term here is essentially a term associated with the gluonic or gauge content of the theory. And we have another term here that is associated with the matter content of the theory. This is to say the quarks. Here we have a sum. This is sum in the number of flavors or type of quarks. This Lagrangian is invariant under transformations of the SU3 group. This is why it is a gauge theory. So if we want to compute observables in general, or any quantity we want to compute them, the information is encoded in correlation functions. If we want to compute correlation functions, we can apply the path integral formalism. But if we naively apply this, we find here an undetermined quantity. And why is this? Well, essentially because when you're integrating over all your gauge copies of the fields, and you have infinitely many, so then you get infinity over infinity. So how you fix this? Well, you have to fix the gauge precisely, and this gauge fixation is made by a procedure that is called the Faddeev-Popov procedure. So as a result of this, you get a gauge fixed Lagrangian, or Faddeev-Popov Lagrangian, that is essentially the QCD Lagrangian. And you have also a term that is associated with the gauge condition, and another term here that introduces new fields. These are the ghost and anti-ghost. These are non-physical fields, but are necessary if you want to make calculations, right? So as a result, once you fix the gauge, you have these 4 interactions. You have here a ghost-gluon interaction. This comes, you have here the ghost, and this derivative here has a gluon here. So this is why you have a ghost-gluon interaction. You have a 4-gluon interaction, a 3-gluon interaction that comes from here, from this term, and you have another term here, a quark-gluon interaction. Okay, but before going on, because we are just starting this talk, let's compare 2 theories. I hope that you are more familiar with this one. So maybe you know nothing about QCD, but you are more familiar with QED. So you know that in QED you have electric charge. So the analogous quantities in QCD is the color charge. We know that the mediator of QED is the photon. The analogous here is the gluon. We know that photons are massless. And gluons are massless, but as we will see in this talk, this is, in my opinion, a more complicated statement. And photons do not have electric charge, so gluons do carry color charge, and this difference here has huge consequences on the theory. In particular, because gluons carry color charge, we have this type of interaction between gluons, a 3-gluon interaction, a 4-gluon interaction. We do not have a thing like this in QED. So this is new, and this interaction leads to these two different plots, let's say. On the left here, what is plotted is the electric charge against the distance, right? And as you can see, it diminishes with the distance. So here, essentially, we have a small electric charge. This is the same to say that we have the intensity of the interaction, in other words, is small. So essentially here, what you can do is apply perturbation theory. So perturbation theory, if I want to compute an observable, this observable is equal to the observable in the free theory plus a coupling that is small, and we have here a correction, and we can continue, right? This is perturbation theory, and here alpha is small. Right? This is perturbation theory. We can do this here in this regime. What happens if we look at QCD? The opposite thing, actually. At short distances, or the high energy regime, remember, energy is the inverse of distance, right? So in the high energy regime, we have small coupling. This is called asymptotic freedom. So here, we can apply perturbation theory, but if we go to the large distance regime, or low energy, the coupling actually blows up here. So we find a Landau pole. The coupling actually doesn't blow up, but if we apply the theory, we find a Landau pole, and this is because we are using perturbation theory beyond its range of validity, let's say. But we have to be careful here, because in this curve, we are using the Faddeev-Popov Lagrangian, this Lagrangian here. And this Lagrangian is not completely justified at low energies. This is to say, in this regime here, this Lagrangian is not completely justified. It's not fully justified. And why is this? Because we have Gribov copies. What are the Gribov copies? Well, essentially, you have your gauge orbit. This orbit represents the gauge transformations of the field, and the gauge condition in this draw is represented by the surface. So ideally, what you could like, is that your orbit would intersect this surface only once. But this doesn't happen. Actually, you can prove that these curves intersects infinitely many times this surface. So the Faddeev-Popov procedure is not justified at low energies. So we need other strategies. One strategy is lattice QCD, where essentially you promote the space-time to a lattice of points, and you make calculations using a computer and Monte Carlo simulations. You have functional methods, such as Dyson-Schwinger equations, functional renormalization group, for instance. You have the Gribov-Zwanziger approach and the refined Gribov-Zwanziger approach that tries to take into account the issue of the Gribov copies. People in Rio de Janeiro have worked a lot on this. We have ADS-CFT correspondence also, and other approaches, but here I want to talk to you about a different approach, and this is a Curci. Yes?
I mean, the two problems that you're mentioning are not two faces of the same coin. I mean, am I right? On one side, you have that perturbation theory breaks down. And the presence of the Gribov copies is not a consequence of that, or...
No.
They are two different things, right? Okay.
Yes, but they are related in some sense, I would say, because as we will see in a moment, this Landau pole appears with Faddeev-Popov. And Faddeev-Popov here actually is not valid, or we do not know at least if it's valid.
It's not
justified. You use a procedure, and this procedure breaks down in the infrared.
Okay, but the
beyond perturbation theory.
The choice of doing Faddeev-Popov is because of perturbation theory, or
no?
Or it's a more intrinsic thing, right?
Faddeev-Popov.
I will check. The fact that you have a gauge invariance that you have to take care of has nothing to do with perturbation theory. It's an intrinsic fact of the theory, right?
Yes.
So the fact that you take care of, let's say, this redundancy with the Faddeev-Popov trick is because you have in mind to do perturbation theory?
No, well, the Faddeev-Popov tries to fix the gauge. It's a gauge fixation.
Exactly.
But this gauge fixation is valid if you do not have grip of copies, let's say.
Fine.
At least in the infrared, you can prove that at high energies, this is not important.
Okay.
But at low energies, it is.
But to me, this looks...
gauge fixation, at least I would say, is not rigorous at low energies.
I totally agree.
Okay.
But I keep... No.
Why, sorry? Well, essentially because of asymptotic freedom, because you have this G becomes very small, and then... Sorry, yes.
Suppose you have a theory
No,
which suppose you have a theory which doesn't have asymptotic freedom. At high energies, is there a Green bar problem or not?
I would say that if you don't have asymptotic freedom, I would say it's a problem, but maybe I am wrong.
So n equals 4 super Yang mills, for example. Does n equals 4 super Yang mills have a Green bar problem at high energies?
I really don't know. I haven't worked on that.
I may be wrong here, but I have the impression that if you calculate the time or some distance between two Gribov copies, this goes to infinity as the coupling goes to zero. So in the perturbative limit, the Gribov copies are infinitely away, and you can always, you only have to worry about one. So effectively, despite the fact that you didn't really fix the gauge, the copies do not appear. Right? In some sense, I cannot make this more formal, but in the perturbative limit, in the weak coupling limit, they don't matter. So Faddeev-Popov is always wrong in the sense that it's never really fixing the gauge, but you can ignore the effects of that in the weak coupling limit. Or maybe people in there can make this more formal.
Thank you.
Just a quick comment is that it's not strictly necessary to fix the gauge to compute things in Yang-Mills theory, because in the lattice, for example, you can compute stuff without fixing the gauge. Right?
I agree, but I would say that this is true if you are using lattice. Lattice is true, but if you want to make an analytic computation or semi-analytic, you... Yes, true. Yes. That's fully true. So, no, but the comment was that the Gastau comment was that indeed, if you want to compute observables, you do not need to fix the gauge, but if you are going to compute a gauge-dependent quantity, you have to fix the gauge on the lattice as well. But I would say that this is true only for the lattice. So we will see that lattice is our benchmark in part of this, for this reason. So let's look at this plot. So this plot comes from lattice simulations, and here I chose one, but we have this plot by many groups working on lattice simulations, and today I think there is a consensus on the lattice community that the gluon propagator features this shape. So essentially what we observe is that at zero momentum, it saturates to a finite value, right? So in principle, if I would naively think about a massless propagator, I would think that it would go as 1 over q squared, at least at tree level, right? So I should expect divergence here. And I do not see this. So in principle, it seems that this propagator behaves similarly to a massive propagator. So what's the idea of this model? It's a model. We are modeling this. So the idea is to add to the Faddeev-Popov Lagrangian a mass term for the gluon. Let me explain this a little bit. This gluon mass term, first of all, is introduced at the gauge fixed level. Why you don't have a mass term here? Well, because it breaks gauge invariance. This is why you don't have a mass term there. But when you are here, you do not have gauge invariance because you are fixing the gauge. So we are introducing a quantity that is not gauge invariant, but we are introducing this quantity for this Lagrangian that is gauge fixed, right? So this is the first observation.
Sorry, do you have BRST symmetry?
No, we do not. This is a problem. We do not have. We have a pseudo BRST symmetry, but it's not nilpotent, and then you cannot do the standard construction. Yeah. So
Probably related to Nathan's comment.
yes.
Can I think of this extra term as a different way to fix the gauge?
Well, actually, this is
Like instead of doing Landau, I do this gauge fixing. But then probably it's related to the fact that you don't have the BRST. So,
well, what I could say about this is that we do not know the origin of this term. This is why I am saying, okay, this is a model. But the thing is, we do not know how to properly fix the gauge, even in Landau gauge. So eventually, this term could appear or could model, let's say, the right gauge fixation. Right? Even you have other approaches. I mean, this Gribov-Swansinger approach, for instance, or refined Gribov-Swansinger approach, where they try to take into account the effect of the Gribov copies. They have a term like this. They have other terms as well. They have more field content in the theory. But as a result of this gauge fixation that tries to take into account these copies, they have a term like this. So this could be a result of a gauge fixation made properly. Maybe you have more terms. We do not know, right? But, yeah.
The reason I wouldn't call this a gauge fixation is that usually what you call is a change to the Lagrangian that does not change equations of motion, even classically, right? And this term changes everything. It's another model, right?
Yeah, and a related question is, what is M? Is M fixed? Is M renormalized? Is M taking the limit to 0?
Well, here I would say it's a bare parameter. Eventually we will renormalize it, but this is a parameter that we are introducing for the bare Lagrangian. Right? Yes, I will go to that. Gastau is saying that it runs to 0 in the ultraviolet. This is true, but I will go into detail with this in a few slides. Right. So this model is normalizable, so it will allow us to make predictions in a very easy way, as you will see. And it retrieves the standard Faddeev-Popov theory at high energies, because it runs to 0, as you will see, but also if you think, okay, it doesn't run to 0, if you look at scales much larger than M, then this term is negligible. And it's a minimal, yeah.
Is the theory unitary?
We do not know.
You don't know?
No.
Can't you just check? A0, does it have negative norm states?
Dave?
There's a paper of Jan de Boer about this, and his conclusion is probably not.
Probably not.
Okay. It's probably not unitary, that's what you're saying? Yes. Okay, that's bad, right?
That's bad. Okay. But I could say that we are in this world is a world where nobody has the unitary theory in the infrared describing everything. Okay, so at least the gauge fixed version, right? So I would like to say also that this is a minimal deformation of the Faddeev-Popov, of the gauge fixed theory, right? We could include here other terms, and we are not. So the idea is to introduce a minimal modelization. This is just a mass parameter. This is trying to model in the propagator, and that's it. And we will see that only with this parameter we can do a lot of things. So how we test the model. This is a model inspired by the gluon propagator. So you can test this model by computing correlation functions that have already been evaluated by the lattice community and compare our outcomes with theirs, right? This is the result. This is the idea. So the first question is how you carry out computations. So we will use perturbation theory, as here you can see, but I will explain why. So let's look at alpha strong. Alpha strong is related to the coupling. G is the coupling. So This is the calculation made with the Faddeev-Popov theory that has, as I already told you, the Landau pole, right? Of course, lattice simulations do not see a Landau pole. What we see is that we reach a maximum value here, and then this coupling starts to decrease again towards the infrared. We can see at this maximum value here, it's around 2, let's say, right? So lambda, the expansion parameter, one can prove that the parameter controlling the perturbative expansion is lambda. The parameter that has to be small is lambda. And this lambda is, let's say, the number of colors, that is 3. Multiplied by alpha, I would say that is 2, but it's less than that, and this is the maximum. And we divide this by 4 pi or 4, 3. So this is, and this is a larger estimation. The maximum value for lambda is less than this. So this is the maximum value. So what I would say is, okay, 0.5, okay, it's not super small, but okay, perturbation theory could work reasonably, so let's test what happens. And this is the maximum value for lambda, right? There is a second plot here. And this plot, I don't want to explain too much, but because maybe it's too technical, but the thing is that essentially what we have here is lambda, this lambda, and here we have m. This is not the mass of the gluon exactly, this is, but it's a parameter related to it. Mu is the energy scale. And what's the important message of this plot? Is that we have 2 zones, as you can see. This zone here are zones where the model features a Landau pole, when you can prove that this model has Landau pole effectively in the infrared. But you have other region here where the model does not have a Landau pole. So your coupling does not blow up in the infrared. Furthermore, you can find between these trajectories many actually, in which the parameter is small at all energies, at all scales. This includes infrared, this includes ultraviolet. So okay, let's take into account these 2 features, one related to the model we are using, another one related to the lattice, and let's try perturbation theory, right? In this framework, looking at these 2 things, it seems reasonable to use it. So I will show you now some results. Yes?
Sorry, why didn't M appear in lambda?
Essentially, what we are plotting there is lambda in comparison to this m for a certain scale, because I didn't tell this, but of course, lambda is a quantity that depends on mu, and you have m that depends on mu. So we have different, depending on your initialization values, I will talk a little bit more about this later, you have different flows for lambda and m.
So just to understand, by putting in M, by putting in that term, you claim the theory never becomes non-perturbative. That's the claim?
Sorry, I didn't get.
By putting in M, you claim the theory never becomes non-perturbative. That's the claim?
I wouldn't say that. I wouldn't say that we can find trajectories, at least in the pure gauge case. This is for the pure gauge case. We can find trajectories, yes, in which your model is always perturbative.
Okay.
You can find some trajectories in which this happens.
Okay, thanks.
So let's start with the pure gauge theory. So we are going to neglect the degrees of freedom associated with quarks, right, to start with. So, and let's compute the simplest correlation functions you can compute. This is the propagator or the 2-point functions. So we have the propagator of the gluon and the ghost. And we will look at this quantity here, G and F. This is called the gluon propagator, actually. And this is the quantity computed on the lattice. And this quantity here is called the ghost resin function. And this is what we are going to compute and compare to lattice simulations. The results I will show you were done up to 2-loop order, right? So we have the 3-level structure, the 1-loop structure proportional to lambda, and the 2-loop structure proportional to lambda square, right? And the same thing with the ghost. So when you do this, you get your Feynman integrals. You reduce your Feynman integrals to master integrals, which are well known, and we know how to compute. We know how to calculate asymptotic limits in the ultraviolet, in the infrared. once you have your master integrals, you have to renormalize, right? Because for those of you who don't know, your results are infinite, so you need to get rid of these infinites and the way of doing that is by renormalizing your results. So you need to introduce renormalization factors for your fields and also for your parameters. In our case, we have two. So now we are introducing the renormalized mass, and this mass will run, and this lambda will run as well. And you introduce your C factors, you need to introduce also your renormalization conditions. And we are going to use these renormalization conditions. Essentially, the first two say that your propagators essentially acquire the tree-level expression at the scale p equal mu, right? This is the first two conditions. And we have these other two conditions that seem more exotic in some way. The thing is that for the Curci-Ferrari model, we have two non-renormalization theorems that essentially says that this quantity here, this product is finite, the same thing with this. Here we are extending the non-renormalization theorem referred to the divergent part. We are extending this to the finite part as well. And once you do this, why you do this? Because these conditions ensure you that your parameters do not feature a Landau pole. So if you use these renormalization conditions, you do not have Landau pole in the infrared. So the propagators depend on a scale mu, but to compare with lattice simulations, we need to fix a scale mu0. So we need to find the runnings, these quantities here, lambda mu and m mu. And this running will depend on initialization values m0 and lambda 0. Why I am saying this? Because we fit the propagators. These are the results. And how you fit this? Well, your parameters run. So you have lambda mu, m mu. What you are going to choose are the values m0 and lambda 0 that are the initialization values that correspond m0 to m evaluated at 1 GeV, and lambda 0, lambda at 1 GeV. This is what you fit. These are the parameters. And a very nice property, yes? No. A very nice property of this model is that the propagators acquire a very simple form. This is the form of the gluon propagator, and this is the form of the gauss dressing function. You can write them entirely in terms of the running of your parameters. Here are the plots. Here we have the gluon propagator. The black dots correspond to lattice data. The blue curve to one loop results, and the red to two loop results. And as you can see, both of them reproduce very well lattice simulations. Here it's not so clear, but the result is improving from 1 to 2 loop. Here it's more clear. Here you have 1 loop, 2 loop, and the result is improving. And you reproduce lattice simulations. Okay, but this is a fit, right? So here I am showing you, we estimated the error. This is the difference between our model and lattice simulations. And what you get is that the difference diminishes. Here is 1 loop, goes in the case of SU3 from 7 to 4, and in the case of SU2 from 10 to 6. As you see, SU2 works worse, I would say, than the SU3 case, and this is something that we will see that happens every time for many quantities, and we have an explanation for this. I will tell you this in a moment. So just one thing, I am telling all the time we, but I wasn't part of this work, right? I am presenting you, this is the introduction, then I will present you some results in which I was involved. So another thing you can test about your results is, okay, you are testing a model, but also a calculation technique, let's say, perturbation theory. So another way of testing if perturbation theory is working is to test the scheme dependence. What do I mean? Okay, you computed your correlation functions using a particular scheme. Well, you can redo the calculation in a different scheme and see what happens. What's the idea? let's say, if two-loop results, in some sense, are more exact or approximate better the exact quantity, then two-loop results should be less sensitive to changes in the scheme than one-loop results. Ideally, your exact quantity should be independent of the scheme, right? So what is the scheme we introduce? It's called vanishing momentum scheme, where essentially you change this condition for this one. I will not go into details, but this is the result. So this is just the gluon dressing function is called this quantity, and this is the one-loop result, and this is the two-loop result. And it's clear here from the plot already that when you go from one to two-loop results are less sensitive to changes in the scheme. So this indicates that perturbation theory seems to be working well, is consistent with our previous results. You can try to measure this scheme dependence, and this is the result, right? So essentially, you are comparing how you change from infrared safe to vanishing momentum in two cases. And as you can see, when you go from one to two loop, if this parameter is smaller, it means that you are less sensitive to changes in the scheme. So it shows that one loop are always more sensitive to changes in the scheme than two loops. Right. So I did participate of this work now. So this is the ghost. Now you have the propagators, okay? What is the next step? Where you can compute 3-point functions. The good thing about this is that you fit the 2-point functions, but you can predict the 3-point functions because you already have M0 and lambda 0, right? So now you don't have more parameters to adjust. So now you take what you have and you make predictions about the 3-point functions and the 4-point functions, for instance. So the first quantity is the ghost anti-ghost gluon vertex in a particular kinematical configuration. This is essentially where this momentum L is 0, right? So, okay, we have many diagrams to compute. A nice feature about this quantity is that it is already finite because of the non-normalization theorem. And as I was saying, this quantity that we are going to compare with lattice simulations is a pure prediction of the model. Of course, this is a complicated computation, so you had to make all the cross-checks you can. So we tested the ultraviolet behavior because we know how it should behave at high energies. We know how this quantity should behave at high and low energies, and we tested that it behaved in the right way. And we also checked the zero mass limit. This is to say the theory with massless gluons. This calculation was already done in the 90s, and we retrieved this calculation. So this, yes, sorry.
So what is a ghost in the lattice?
What is the ghost?
Yeah, you haven't gauge fixed, so what ghosts are you talking about in the lattice?
No, here I'm comparing with gauge dependent quantities, so these are simulations in Landau gauge.
On the lattice?
Yes.
Okay, so you're gauge fixing the lattice?
Yes, they do that, but many people do this on the lattice community.
So what action do they use when they gauge fix on the lattice? So
they start with QCD, right? With the action of QCD, and they gauge fixed by...
With Fadeev-Popov?
No.
So
with
what's a ghost?
No, with QCD, right?
What's a ghost if you don't have Fadeev-Popov? I don't know what a ghost means.
I really don't know the details.
No, but a ghost comes from Fadeev-Popov, that you know, right?
Yes, I get your question. It's a good question, yes. But I don't have an answer at this moment, but good question. Yeah. So this is the result for SU3. So the lattice already has large uncertainties, so it's hard to tell which one is better. But the good thing is that, okay, this is pure prediction, right? You're getting a nice result, even though it's a pure prediction. We are not fitting anything here. We do not have a free parameter. You can do other thing that are associated with these bands. Essentially, what you do is you check your relative error between, for instance, in the case of this pink curve, is the relative error between
sorry, I'm not from the field, and
Yes.
I'm not an expert at all, but with that huge error bars, how you, I mean, it's hard to, let's say, to believe that points are reproducing, let's say, that shape that you have in the curve, right? I mean,
I agree, it's hard to tell.
In principle, any curve will fit decently well, right? I mean,
yeah, I agree. But
Okay.
it's what we have. We will see other quantities that have better lattice
Okay.
data.
Okay.
This is the first plot, but it will get better.
Okay.
But this is what we have up to this moment. So what we can say, we cannot say we are reproducing, okay, this is like, I agree. This is maybe too strong. But okay, the orange curve could be whatever, right? This is a two-loop calculation. It could go like for 2, 3, whatever, it doesn't. So this is a good sign.
Okay, so the good sign is that your curve doesn't explode, let's say.
For instance,
okay.
Yeah. There's a second good sign that is associated with these bands. So why we are drawing these bands? Essentially, these bands are associated with the difference between one order and the next one. So for instance, the pink is associated with the difference between the tree-level calculation and the one-loop. And the orange is the difference between one-loop calculation and two-loop calculation. And what we observe is that this band from 1 to 2-loop becomes smaller. And this goes in accordance with a perturbation theory that is doing the job, right? That is working well. SU2, lattice data, is better. This is SU2. And our results are not better, as you can see. So this is the result. It doesn't seem that two-loop is working better in this case. But OK, this is not a surprise. As you already saw, when we saw the propagators, the SU2 case worked worse than the SU3, right? And why is that? Well, you can look at the expansion parameter here. And the expansion parameter in the SU2 case is larger. So if you have a larger parameter, perturbation theory works worse, of course. So this is a pure prediction. So you can try something less ambitious. Instead of trying to predict your vertex, you can try to fit two-point functions on the vertex at the same time. And if you do this, you get this. So this is nicer. You can try to compute the scheme dependence, and in this case, again, SU3 seems to work, like it diminishes, but it does not diminish in the case of SU2 here, right? So again, SU2, we don't know. We do not know. You can look.
It looks that
yes.
lattice data are better for SU2. They have
Yeah.
smaller error bars.
Yes.
Why? Why lattice instead prefer
I think
a small
SU2,
n?
because n equals 2, I think is easier to do.
I see. Okay.
You need less.
Computational power, you mean?
Exactly.
Okay.
Yeah. So let's look at the 3-gluon vertex now. So this I didn't draw the vertex, but okay, we are looking at this. All right. And we will compare this at 2 loops with the lattice that is non-perturbative, right? And again, we are considering a particular kinematical configuration. I will not go into details. This is the quantity we are computing that has already been evaluated on the lattice. We have many diagrams to compute. And here you have to be careful with the renormalization. So you need to introduce your Z factors. So now your 3-gluon dressing function, we call this is the quantity evaluated on the lattice, depends on this renormalization scale mu. So this is the results. And here we are comparing with 2 sets of lattice data, because specifically here in the infrared, you see that the results are quite different. So we prefer to do the analysis independently in the 2 cases. Black curve is the 1 loop, blue is the 2 loop, right? This case, it's hard to tell whether we are improving or not, but this case, it's clear that 2 loop is improving with respect to 1 loop. You can see this here in this error table. Essentially, look at this here, this error. So this error is associated with this plot, and you see that it goes from 12 to 6, let's say. And here, it diminishes. It's not so big, the difference, but still we improve from 1 to 2 loop. So it seems that it's doing the job. Again, this is a prediction. Here we have an overall normalization factor that we adjusted because you have to renormalize this. And the renormalization lattice community uses is different from the renormalization we use. So there is a renormalization constant between both results. This is SU3. When you go to SU2, you get this. So in this case, the result again improves when you go from 1 to 2 loop. In this case, the scheme dependence is consistent with the perturbative treatment, both for SU2 and SU3. So in this case, we observe that the scheme dependence diminishes in all cases. So a nice feature of this model is that, okay, you can see that we can reproduce lattice simulations, but it's also a simple model. So you can get analytic results in many instances. For instance, I didn't wrote them here, but you can get analytic expressions for the ultraviolet and infrared behavior in all cases. And this is an example of the infrared behavior of the 3-gluon vertex. There is a sort of debate, depends who you ask about, if there is a zero crossing here, if this quantity becomes negative or not. Here, it doesn't. Here, it's always positive. But here, it takes negative values here. Right? So we have a zero crossing, or we don't. In the case of Curci-Ferrari, it seems strange, right? Because at 1 loop, you clearly have a zero crossing here, but at 2 loops, it seems you don't. So we had the question, do we have a zero crossing? We don't. And we do. You can prove this relation at all orders of perturbation theory. Essentially, I want you to look at this term, right? And this term shows that you have a zero crossing eventually. Right? This mu is a fixed scale, right? So eventually, if p is small enough, your log becomes negative, and you will have a zero crossing. So you can also compute the 4-gluon vertex, right? These lattice results are not very good, but this quantity is very hard to compute on the lattice. Actually, these results here are from this year, right? And you can see that this is a prediction again, and we get nice results. This is at 1 loop only. Okay, all of this for Yang-Mills, without quarks. What happens when you include quarks? Well, in this case, first of all, perturbation theory shouldn't work very good. Right? This is the first statement to say. So we know that this coupling is larger, the coupling controlling the quark sector, right? So perturbation theory shouldn't work so good. Additionally, we know that certain phenomena, such as the spontaneous breaking of chiral symmetry, are non-perturbative in nature. So if you want to reproduce this, you need to go beyond standard perturbation theory. So the results I will present you anyway are perturbative. We are using plain perturbation theory, right? But the idea is to distinguish. We believe that certain quantities could allow, eventually, a perturbative description, and others not, and we would like to test this within the model.
Sorry.
Yes?
Just the point about some purely perturbative techniques. You claim confinement you can understand using purely perturbative techniques, just to understand what you're saying?
I would say that no.
No, but confinement, you don't need quarks for confinement.
Well, you have, yes. Well, there's a very recent work, actually, like 2 or 3 months ago, where they study confinement in pure Yang-Mills theory. And I think to some extent they use perturbation theory, and they get to, for instance, they compute the string tension. They compare with lattice simulations, and it coincides very well.
So you think it can be understood perturbatively?
Yes.
Okay.
Yes. Up to a certain extent, yes.
Okay, thanks.
So again, I'm going to show you the results of the 2-point functions, right? So essentially, we have the same things I showed you before, and I have things.
A very naive question.
Sure.
What does it mean, confinement without quarks? I mean, from the beginning of your talk, I understood that confinement is a property that quarks stay together, right? So if you don't have quark, what is confinement?
Well, the gluons are confined, right? Anything with color is confined.
You can have glue
I
balls
see.
eventually.
Okay.
Right. Yeah, you cannot find a gluon in isolation. Welcome. Yeah.
No, just to add that also finite temperature Curci-Ferrari shows these confinement features about center symmetry breaking, for example. So.
Yes. I'm going to talk a little bit about finite temperature at the end, but yeah. So in this case, we have the ghost, the same quantities we already saw before, and we have new quantities, the C factor that we are going to call the quark dressing function, and this quantity that is the quark mass, essentially. So these quantities, anyway, we are going to compute them again, because now we are going to compute them in the presence of quarks. So again, you have to introduce your renormalization conditions, right? So we have essentially the same conditions that I showed you before, and we have now new conditions that are associated to the quark sector. And okay, here you can see the title, global fit of these three functions. So we have four functions, right? D, F, Z, and M. And we will start neglecting this. Why? First of all, because we believe that this quantity is non-perturbative, right? So we are going to use perturbation theory, so we start by studying only these three. And you perform a fit, similarly to what I showed you before. Now you will have M0, lambda 0, and anyway you will have M0, right? When I say we are not going to fit this, I mean we are not going to see lattice data for this. We are not going to try to reproduce lattice data for this quantity. So from this, you get the runnings, and these are the fits. So the first two are essentially the gluon and the ghost. This is not surprising. This was essentially okay before, right? Still working, very good, but it's not surprising, I could say. This one is quite surprising here. This is the C factor. This is a quantity associated with quarks. Why is surprising? This is one loop. And these black dots here are lattice data. So at one loop, the result is not good, right? So why at two loops is so good? I mean, it goes from very bad to very good. So what happens? Well, we believe that in this case, when you compute this C factor, and you have massless gluons, right? The standard theory, massless gluons, this C, the correction at one loop order, is 0. It's identically 0. So your leading correction is the two-loop one. Right? And we believe that here is happening something similar. When you put a mass, it's still a small mass, still your dominant correction should include the two-loop correction. This is the explanation we have for this. Right? So, and it works pretty good. You can see here the differences in the errors. Right? This is the one loop, this is two-loop, and two-loop is very good. Yes, here I don't know if they are so much smaller than, because here they are computing the 2-point functions, right?
Yeah.
Here is 2-point functions. So we should compare this with this.
Okay.
So yeah, I don't see the difference is so big. So I think it's more or less equivalent. It's because you are computing 2-point functions. When you increase the number of external vertices, let's say, it becomes more complicated and it's harder to compute.
So I just want to clarify, when you say two loops, you mean the one loop plus the two loop?
Yes,
okay.
And the tree level also. Okay. So this, anyway, we have 3 parameters here. So we have these two, but we also have another parameter, right? and we fit this parameter. So it should be nice to introduce some information about the quark mass, because we have lattice simulations for the quark mass. So the idea now is to determine these two quantities from the fits of D, F, and C, and M0, right, the quark mass at some energy scale, to be equal to the lattice data, in particular to a value of the lattice data in the UV. Why this? Because what we would like to have is to generate mass. You have small mass in the UV, and you would like to generate a lot of mass in the infrared. This is the spontaneous breaking of chiral symmetry, right? You have little mass in the UV, and you generate a lot of mass in the infrared. So what we want to see is what happens if we have little mass in the UV. Can we generate mass in the infrared? Can't. We can't. Let's see. Yeah, if you have 0, for sure you cannot. Yeah. But something I didn't tell you, actually, like, because you have various sets of lattice results. You have, in particular, here you see it says M pi 150 MeV. So you have this that is closer to the physical value of pi. So this is where you have little mass in the UV, but you have another one that is this one, right? In this case, you have artificially large masses in the UV. And this is important in this case, because here this one corresponds to the case M pi equal 150, and this one here, M pi equal 422 MeV, right? So in the case that we have artificially large masses at high energies, we can generate a lot of mass in the infrared. We cannot do this if we have small masses in the UV, if we are closer to the physical case, let's say. This is reasonable, again. But it's good to know that if you have large masses in the ultraviolet, you can generate perturbatively a lot of mass in the infrared. You can see this here. The important number, I would say, is this one, right? Here it shows that the error is huge. 1 to loop, it's huge, right? You need something more than perturbation theory to reproduce this. But here, okay, it's still big, but more reasonable. So you can do this, well, by choosing this. You can try to do just a global fit of everything, and we obtain something quite similar than these plots. So then one could ask, the Curci-Ferrari model is not able to reproduce the quark mass in the infrared, but this is not true. The thing is that you need to go beyond perturbation theory, because here you have spontaneous breaking of chiral symmetry, and this is a non-perturbative effect. So what you can do is to try a non-perturbative technique, part of it at least. The idea is to treat the pure glue sector perturbatively, because it seems that it is perturbative up to a certain extent, even at low energies. But to leave the quark sector non-perturbative, you need something more. So essentially what they did in this work is to do an expansion in 1/NC. That is a usual expansion, right, in this area at least. When you combine these two techniques with the Curci-Ferrari model, you get this curve. So you start with little mass in the UV. Essentially, you are over the lattice data here, but you can reproduce all the mass in the infrared. So we can reproduce the mass, but you have to go beyond perturbation theory. So a final comment. The Curci-Ferrari model has also been used to study QCD at finite temperature. In particular, they have studied the critical temperature and the transition in pure Yang-Mills theory by using this model, and they have reproduced lattice simulations. And recently, some aspects of quark confinement, in particular the string tension, for instance, has been computed by using this model, and also the results agree with lattice simulations. So to summarize, the Curci-Ferrari model is given by a simple gluon mass extension of the textbook Fadel-Popov action in Landau gauge. It is motivated by the decoupling behavior of the gluon propagator on the lattice. It is proposed as a model to study the infrared of Yang-Mills theory and QCD, and lattice simulation suggests that perturbation theory is a good starting point, right? So I show you results for several correlation functions evaluated at 1 and 2 loop that successfully reproduce lattice simulations, right? In the case of pure gauge theory, the results support the validity of the perturbative model in SU3 gauge group, and to some extent also in the SU2 case. The results show that the SU3 case is systematically better than the SU2 group, right? And a very nice feature of this model is that it also enables us to study at the analytic level the infrared divergences, the infrared behavior of these correlation functions, the ultraviolet behavior, right? And in the presence of quarks, up to a certain extent, right? These quantities are perturbative, but the quark mass is not. Anyway, in this case, you can reproduce it in the Curci-Ferrari model, but you have to go beyond standard perturbation theory. So, obrigado.
Thanks a lot, Nahuel.
You're
More
welcome.
questions?
So you mentioned that confinement has been studied in Yang-Mills theory using this model, and you obtained string tension compatible with lattice simulations, right?
Yeah.
So in this case, I think you computed the fundamental string tension, right?
Yes, I think so. I'm not very familiar with this work, but...
Yeah. Because one important property of confinement in Yang-Mills theory is that adjoint quarks are not confined. So the adjoint string tension should vanish. So did you check that?
I don't know really, but I don't think so. I mean, this is the very first work, and essentially they studied the flux tube between two static quarks.
Yeah, the fundamental flux tube.
Yes, yes.
Okay. So it's a bit too strong to state that this model is able to capture the confining properties of the
for sure. Yes, yeah. Yes. This is why I said this is the first study about confinement that points in a good direction, but that's it.
Okay, thanks.
You're welcome.
More questions, comments? Okay, we had many during the talk, so
yeah,
probably people are satisfied. So let's thank our speaker again.